continuing on with our statistics, we had a quick look at these before. So you have your population parameters and your sample statistics. Very important that you understand what they mean, because we are going to be using those mostly out of laziness. So we generally look at the population. We won't be able to survey the whole population. So what we do is we get a random sample. So every member of the population has the same chance of being selected. And we use some statistics, whether it's from categorical data and we tell you the sample proportion, or numerical data and we tell you the sample mean. So we give you the statistics and we use those statistics to estimate what the real answer is, the real percentage of the population, or the real mean of the population is. So that's what we do all the time, and that's why the topic is called statistics and not parameters. We use a sample, not the whole population, in order to do things. So some of the things that we do is we do confidence intervals, we do z-scores, etc. So the first thing that I want to look at is a confidence interval. And we get our statistic, and that could be x bar or p hat. That's if it's numerical data, that's if it's categorical data. And what we do is we use some maths to create an interval around the statistic. So I'm just giving you the outline here, not doing any maths. And we create the interval, and then we tell you that, we're pretty sure that the real parameter, not statistic, lies within this interval. So we use the statistics, we do some maths to create an interval, and then we kind of, I'm pretty sure that the real answer for the whole population lies within my interval. Now, obviously, I'm just giving you a basic outline there. I'm going to be a lot more specific as we go through this. So if we look at this, we're doing inferential statistics. So we're surveying a sample. We use the sample to infer what we think will happen for the whole population. How confident can we be? How close can we get to the real answer? Well, it just depends on, the size of the sample, the maths that we do, etc., etc. But the only way to get the perfect answer is to survey the whole population. So if we have a look at this here, we're a guy on the TV and he's like, we'll take a look at tomorrow's weather. The temperature will be between 40 below zero and 200 above. And you can see there Garfield's like, this guy's never wrong. Well, the reason he's never wrong is because he's created a huge interval. That's pointless. We don't want a massive interval. Sure, if we want to be 100% sure, we either survey the whole population or we create an interval that's so huge that the real population parameter has to lie within it. So we know we're not going to be correct 100% of the time. So what we're going to do is we're going to create a confidence interval. And so we're going to use our statistic. We're going to add and subtract a little bit. For you at Leaving Cert, it's always going to be 1.96 times your standard error. Now, the reason that it's always 1.96 is because we are always going to be using a maths to do with a 95% level of confidence. And I mean, without going into, a whole pile of detail, if we're using a 95% level of confidence, the 1.96 actually comes from this table here. So the information as to where that 1.96 comes out of is to do with, your Z scores and the percentage of the population. So this is actually a Z score that's linked to 95% either side of the mean. The standard deviations above and below the mean. In college, it's possible that you wouldn't be doing a 95% you wouldn't be doing a 95% level of confidence to do with your interval. So if that's the case, if you were in college, this number would change depending upon if you're doing a 95% or another common, so 95%, another common one would be 90% or 99%. So if it's 95%, it's 1.96. If it's 99%, it'd be something different here. If it was 90%, again, it'd be something different here. But because for your leaving cert, you're only looking at it from a 95% level of confidence, then this 1.96 is always going to be there. So you're going to get your statistic. So you survey a sample. Maybe you ask them a question that's going to generate numerical data. So the statistic you're going to get is going to be the mean of the sample plus or minus 1.96 times your standard error. Well, again, this is in your log tables. If you go to this page here, here's your standard error of means. So yeah, it was a numerical data that was generated. So it's the mean that we use plus or minus 1.96 and then times the standard error of the mean, which I'm literally taking from the log tables. That's your standard deviation, and that's the number of people that you surveyed, so the size of your sample. You would fill that in and it would create your confidence interval, your 95% confidence interval. If the question that you happened to ask was like something that generated categorical data, well then your statistic would be p hat, the proportion of the population that have brown hair, or whatever it is that you've asked, plus or minus 1.96 times, this time, it's your standard error of proportions. So I'm using this formula here. Again, it's in my log tables. P bracket, it's the square root of P bracket 1 minus P all over N. And again, this being P, the population proportion. So that's just the general idea of your confidence interval. And we want to work with this, so we can have a look at some questions to do with this. Let me just see if I can find one. Okay. Oops. There's a good question. Take your time, have a read, pause the video. The question says, at a 95% level of confidence, they want you to create a 95% confidence interval for the proportion of the 100,000 radios that are damaged, given that a random sample of 200 radios is taken and 34 of them are damaged. So obviously pause the video, take a good read of the question, and then have a go yourself at doing the confidence interval if you'd like. I'm just going to continue on here and do the confidence interval. So, there's a certain amount of radios damaged after a fire. There's 100,000 of them. I couldn't be bothered counting the 100,000 and seeing exactly how many radios are damaged. So I get a sample of 200 of them and 34 of those are damaged. If we think about it, what's the data that's generated? Well, the question is the radio damaged? The answer is yes, no. So that's categorical data, which means that we'll be using p hat. So p hat plus or minus 1.96 times the standard error of proportions. P hat in the question, we have 34 radios out of 200. So there's the fraction or the percentage or the proportion. If you feel more comfortable, you can work in percentages just to make sure you're completely accurate. Plus or minus 1.96. And then we don't have P in this situation. We don't have the answer to that. If we did, we wouldn't be doing this. So I'm going to have to use P hat. So it's not going to, it's not perfect maths that we're doing here. We're doing our best, working with a sample, trying to figure out what is going on. Okay, and you should just throw that into the calculator. Take your time, work it out. And eventually you should end up with, I think, this. So my interval is created by getting my statistic, adding this, subtracting this. So I get my p hat, I add this on, and I get the upper level, 18.8%, and I get the lower level. Oh, sorry. 18.8 is my lower level, 18.8% and 22.2%. I've now created my interval, and what do I think? From my interval, I reckon at a 95% level of confidence that P, the real number, the real percentage of radios that are actually broken lie between 22.2% and 18.8%. So, somewhere around 20% of them seem to be damaged. So that's part A. If you want to, you can go back and have a look at part B. Part B says, find at a 95% confidence interval the number of radios that are damaged. Well, that's pretty straightforward. If we think that 22% of them are damaged, well then what's 22% of 100,000? Well, that's 22,200. So it's approximately 22%. Well, that's that. Now I'm going to change this. This is the number of radios that are damaged. And the lowest number that are damaged from my information is about that. So it would be worth doing a few more questions. Plenty of questions that you can find in your book to do with it. I would be looking at I reckon it'd be worth looking maybe at 150. Page 150. I don't particularly love the questions from the papers myself, but I go to, or from the book myself, but go to the papers, find a question that just asks for a 95% confidence, 95% interval. And sorry, I'm just looking for another question here, just to even put up here. Nope. I'll find one eventually. Here we go. Try that one. Again, pause the video and read it in this situation. So I'm going to continue on now. I've obviously read this question. It says form a 95% confidence interval for the mean number of kilometres travelled. Well, a confidence interval, when the question is generating numerical data, because it was like how many kilometres was travelled per litre of fuel consumed. So in this question, I'm going to do x bar plus or minus 1.96 times my standard error of means. So x bar in this situation was 13.52 plus or minus 1.96 times the 2.23 over root 150. So you use your statistic, you add on a bit, you subtract a bit to create your interval, and then you're pretty sure that mu lies within your interval. That doesn't mean you're absolutely correct, but we have a 95% confidence interval. We're not like the guy on the TV that Garfield is watching. It's not 100%, it's not this massive interval, so we're not 100% confident that mu will lie in between it, but we are 95% confident that mu will lie in between here, these two. Again, you could try a few more questions. There's another good one. So just pause that, work at it, and see how you get on with it. Again, pause the video. I'm just going to show you where I went with the question. So you create your interval, and then that's part B there.